In this video, we're going to look at rates of change. So the first thing I want to do is look at the definition of the average rate of change. The average rate of change of f of x with respect to x for a function f as x changes from a to b is, and then we have this definition, f of b minus f of a all over b minus a. That should look familiar because that particular definition is actually our definition of slope. What we mean by average rate of change is essentially the same thing as slope, which is the, I'm going to say, rate of change between two distinct points. This also in calculus, when we say the rate of change between 2 points is also called the slope of the secant line. So that's something important that you'll want to make sure to make a note of, put a star next to that so that we can see there. Down below, I've given y'all a picture, and I'm sorry, a little bit of this is blurry, but we have our function f of x, and the f of x function is the curved blue line that you see here. So that's my f of x function. And then we picked a couple of points, a and b, as far as the x values that were associated with the a couple of points on the line. So we said if we pick this x value of a and we pick this x value of b, then we'd get the associated f of a. I'm going to go ahead and make that clearer so you can see it. F of a values and f of b values. And so those ordered pairs there would essentially be ordered pair a, comma, f of a. And then on this one, b and f of b. All right, so there's the idea. So what we did is we looked at two distinct points that were on my function f of x, and then we drew a straight line, which is now called the secant line, between those two distinct points. And we see that line is a straight line. And so the slope of the line is given by this formula. That would be the slope of the secant line. And it would be the average rate of change between the two distinct points, a, f of a, and b, f of b. All right, so on here it says find the average rate of change of the following function over the given intervals. So on this one, part A, we have a quadratic function over the interval from -2 to 0. On these types of questions, you don't have to graph, but we have to use basically just the definition. And so on here, what we're going to do, I'm going to go and abbreviate average rate of change as AROC. Sometimes we get tired of writing that, so we abbreviate it instead. And so I'm going to start this off by saying average rate of change. And then I'm going to go ahead and write my formula for that. And then I'll plug in eventually the specifics for my formula. So my formula is the slope formula. It's f of b minus f of a, and then all over b minus a. Now, what were a and b in the formula? So if we come back up, the a and the b in the formula are my x values from what I can see down here on my graph. And so on there, we notice that my a is my leftmost x value here, and my b is my rightmost x value there. That means that if you're given an interval of some kind, then the a is the leftmost value in that interval, and the b is the rightmost value in that interval. And so on here, what we'll do is the top is telling us to evaluate the function that we've been given. So here's the function that we've been given, specifically at the values a and b. So on the top, I would say f evaluated at, what's the value of b? That's 0. And then minus f of, what's the value of a? That's -2. So eventually here in a bit, we'll plug in those values into our function and actually evaluate. On the bottom, it says it's just the difference of my x values. And so there I would do 0 minus, be careful here with the signs, -2. All right, so the function is 2x squared minus 3. So now I want to evaluate that function at 0. When I'm evaluating functions, specifically on the average rate of change formula, you have to be careful. We see in the formula we have that negative sign. So that means that whatever function comes second, we generally have to come in and insert our own extra set of either parentheses or braces, depending on how you want to write that. So you have to be careful because otherwise that negative doesn't get distributed if that second piece is more than one term, which in this case it's going to be since our function is more than one term. So let's go ahead and come in here and evaluate. So f of 0, that's going to be 2 times. And then anytime I'm evaluating a function, I generally put a parenthesis wherever x was and then insert that x, and then that'll take care of any kind of sign problems that I might have. So 2 times 0 squared minus 3 is the function evaluated at 0, and then minus, and then I'm going to be careful to put an extra set of either a parenthesis or a bracket there, and then f evaluated at negative 2. So 2 times parentheses negative 2, and that's to the second, and then minus 3, and then I'm going to close off that bracket. And then all of this is over 0 minus negative 2. Well, negative 2 is positive. 0 plus 2 essentially is just 2. All right, in the top I have 2 times 0 squared. 0 squared I have to do first because of order of operations. 0 squared, 0. 0 times 2 is 0. So that leaves me just the negative 3. And then I'm going to go ahead and leave those brackets until I figure out the value of what I have on the inside. On the inside, order of operations indicates I have to do the negative 2 all squared first because that is an exponent. And so negative 2 all squared would be positive 4. So I would have 2 multiplied by positive 4 and then minus 3. All of this is still over 2. All right, on the inside of the brackets now is the next place I look, order of operations. So I'd have 2 times 4. 2 times 4 would end up being 8. So here this value would be 8, and then I have a minus 3. So the inside there would end up being 5. So essentially here I have negative 3 minus the inside piece of the bracket part ends up giving me 5. So I could get rid of the brackets now and just say 5, and then all of that over 2. Negative 3 minus 5 is negative 8. Negative 8 over 2 is negative 4. So the average rate of change between those 2 points for that function on that interval is negative 4. That's indicating 2 things for me. We have the actual value of negative 4. The sign on that value indicates that we have a negative correlation. In other words, whatever rate of change is indicating a drop or a decrease. And then obviously there, the 4 is indicating at what speed that decrease is happening. All right, the next one, we're going to look at a different function. So on here, once you've learned average rate of change and you've got the formula, really the only other problem is just trying to make sure that we're okay with whatever function that they throw at us. So on the first one, they threw at us a quadratic function. We were okay there. On this one, they're throwing at us a square root function. So my f of x is square root of x. And on this one, notice that they give you the information in a different way. On the prior problem, it said on an interval from negative 2 to 0. On this one, it says between x is equal to 1 and x is equal to 4. It's the same information, just given to you in a different way, and you have to be able to adjust to that. Okay, so first of all, we'll say, what are we finding? We are finding average rate of change. So AROC. And then our formula for that. A general rule is until you learn a formula real well, write it down every single time you use it, and that will get you that much further down the line as far as memorizing it. So we're going to say f of b minus f of a all over b minus a. All right, in this particular problem, it's good to label what a and b are. So remember from our drawing up above, a is the leftmost number and b is the rightmost number. And so on here, for this particular one, do we see 1 is smaller than 4? So for that, a would be the 1 and b would be the 4. It honestly doesn't make a lot of difference. I'm going to say the order in which you label these, as long as you're consistent with the way that you plug them into the formula. But I'm going to be consistent with what I showed you in the drawing up above. And I'm going to say easy to say, I know A is always my small number and B is always my bigger number. So on here, we'd say F evaluated at 4 minus F evaluated at 1. And then all over 4 minus 1. And then now we use our function and actually plug in. So our function is square root of x. So f evaluated at 4 would be the square root of 4. And then minus f evaluated at 1 would be square root of 1. And then 4 minus 1 on the bottom is 3. So here, square root of 4 is 2. Square root of 1 is just 1. This will be all over 3. 2 minus 1 is 1. And so this will be 1 over 3 as my average rate of change. That tells me two things. The actual value, 1/3 is the average rate of change. We see that it has a positive sign. That means that whatever is happening here on this function, we have an increase as far as the rate of change. And then the 1/3 would indicate the rate at which that increase is occurring. All right, part C, I wanted to look at more of an application type problem. So this one says, let S of t equal negative 2t squared plus 15t represent the height in feet of a paper ball thrown in the air, where t is in seconds. Find the average velocity of the ball from t equals 4 to t equals 6 seconds. The first thing to notice on this particular problem is they're not asking me to find the average rate of change. You don't see that wording in the problem, but they have asked you to find the average velocity. You need to know that that's the same thing as the average rate of change. Okay, so that's an adjustment that you're going to need to make sure that you understand. That, you know, if a word problem is talking about an average velocity, it's the same thing as the average rate of change. Okay, once again, they gave me from t equals 4 to t equals 6 seconds. Those are going to be like my x values. So notice in this particular problem, instead of having x as our variable, we have t. And so on here, remember the smallest one is my a value and the largest one would be my b value. So on here, we're going to say we're finding average rate of change. All right, the average rate of change is the same thing as the average velocity. So I'll abbreviate that, AV for average and then VEL for velocity. And that is the same in this particular case. Notice that they're not using f of x, they're using s of t. So we need to adjust our formula for that. And so we're going to say it's going to be s of, remember we always do the big number first, so s of b minus s of a, and then all over b minus a. Our general formula says f of b minus f of a, but we want to use the name of our function. So in other words, in this particular problem, because they're saying, hey, my function is called s of t, my function name is s. So I want to make sure to use s when I go plugging in the formula. The reason they do that is like on certain problems you have more than one function. So you might have like an f of x function and a g of x function and a q of x function. And so in that case, you want to be specific, you know, which function am I using? I know we only have one in this particular situation, but it's good form to practice making sure that we use the correct terminology. All right, for this one, our b was 6. So we're going to have s of 6 and then minus s of 4. 4 was the a, and then we'll have 6 minus 4 there on the bottom. All right, and then from there, we need to plug into the function. All right, for this one, we have, looks like a quadratic function that we're plugging into. We notice there on the second piece, we're going to have to go in and put brackets here since our function contains more than one piece. Notice on the problem prior, I did not do that. And the reason I did not do that is our function was only one piece. So it was not necessary to put brackets over here around the f of 1 since I was only evaluating one piece there. It's always safe to put them, if you want to, around that s of a part. And then that way, if you need them, you've got them. If you don't need them, it's not a problem. All right, so we want to evaluate s of 6. That means go to this function and plug 6 in. So it's going to be negative 2 parentheses, plugging in 6. That's going to be squared plus 15 multiplied by 6. So there's s of 6. And then minus, I'm going to use a bracket. We're now going to evaluate s of 4. So negative 2 multiplied by 4 squared plus 15 times 4. And all of this is over 6 minus 4. 6 minus 4 is 2. So we've got that there. All right, and then from here, we're going to go through and evaluate our different pieces here. And so let's see here. For this first piece, I'm going to do this all together. You guys have your calculators, and so if you want to do this all together, you definitely can. The 6 squared is going to be 36, and then 36 multiplied by your negative 2 is going to be negative 72. All right, and then we have 15 times 6. 15 times 6 is 90. And then minus, we still need brackets over here. We're going to have 4 squared. 4 squared, 16. 16 times negative 2 is negative 32. And then over here we have the 15 times the 4. 15 times 4 is 60. And then all of this is over 2. All right, I'm running out of room a little bit, so I'm going to wrap around here. All right, from here, let's see here, negative 72 plus 90, that's 18. And we still have the minus. On the inside of the brackets, we have negative 32 plus 60. That's going to be 28. We can now get rid of the brackets since that number was positive, and then all over 2. Okay, and then 18 minus 28 is negative 10. And then negative 10 over 2 is equal to negative 5. Now, the other 3 questions that we worked didn't have units with them. But on this particular problem, it's a word problem that did have units. Notice here that we were saying that S of t represented height, specifically in feet, and then t was in seconds. All right, so notice that on this particular problem, in the top, we subtracted S of b minus S of a. Well, since they're functions evaluated at particular values, the function represents height, specifically in feet. So on this one, in the top here, get rid of that, these units would be feet. And then notice in the bottom, we subtracted b minus a. B minus a were seconds. And so on that one, if we were looking at the units that we had here in the denominator, that would be seconds. And so on this one, when we get done, the negative 5 is in the units feet per second. So it's important that when we have a word problem that we make sure we put the units on when we get finished here. So this one, we know that we have a negative correlation, meaning that something's decreasing. It's decreasing at a rate negative 5 feet per second. All right, so what we've looked at so far is we've looked at average rate of change, which we know to be the slope of the secant line. Secant means that you went through 2 distinct points. All right, now we have a definition. This one is especially important. This is going to be half of our semester, essentially. Half of the semester, we're going to look at this particular idea, and it's called instantaneous rate of change. Okay, that's the rate of change at a single point, or the slope of a tangent line. So what I'm going to do right quick is I'm going to come down below before I get into the other part of this, and I'm going to look at a graph, and I'll show you basically what's going on with the graph. So once again, I used as f of x this nice curved line in here. So that was my f of x function. And so on there, what I did is I said, hey, we already looked at a slope of a secant line. And so if we pick a point here and a point up there, we know we can find the slope between the secant line, which is the straight line that connects those 2 points. So now what we're going to do is use this idea. We're going to make essentially points on f of x become closer and closer and closer to this point where I have the x value being a, and think about secant lines through those. So now I'm going to look and say, okay, instead of looking at the green secant line, let's pick a point a little closer here so that that point's closer to the original point there. So the distance between those 2 is closer. And then look at a secant line between those 2 points. We obviously could find that. We'd have here a different value here. Let's call that a B1. Okay, and then we're going to do the same thing. We're going to come down and do different values. So let's see, make this point now even closer to this point here. Draw a secant line between those 2 and continue with that pattern. So now we're going to have a different B. We'll call that B2. And continue with that pattern until you get, I'm going to say, as close as you possibly can. So different B value here to this A. So you're making these 2 points super close together, and you're doing secant lines through those. Well, eventually what's going to happen is you're going to end up, I'm going to say, infinitely close here to A. So you're going to keep doing this and finding values closer and closer and closer. If you could actually get to A, then you'd have a single point and then the slope of that particular line. And that line right there is what we call the tangent line. So if you can ever get your line to go through a single point as opposed to 2 points, then that's called a tangent line. There's a limiting process here. So in other words, realistically, if you're using 2 points and you're trying to get infinitely close to this x value A, you'd never be able to get there. Because think about, like, if you're halving, you can always half a distance. So as long as your distance is not 0, which is not, because to start out with, we have 2 distinct points. If you're halving your distance, you're just infinitely getting closer and closer and closer to A. So what we're saying is we're saying that the distance here, and we're going to call that distance H, is getting close to 0. So we're trying to make that distance as small as we possibly can. All right, and then when we do that, we're getting close to what we call a tangent line. And the tangent line represents the line where that if you take an instantaneous rate of change, it's the rate of change at a single point instead of 2 points. So I'm going to come back up and let's look at what I skipped over. So think of finding an average rate of change, the rate of change between 2 points, where you let the 2 points become very, very close together. If the distance between those 2 points is h, then we want the value of h to be very close to 0. The formula, and this is super important, for instantaneous rate of change, also known as the derivative, is given by f prime of a. The prime is indicating we're taking instantaneous rate of change, or the derivative. Specifically, we want it at a. So notice here, we didn't need an a and a b because we're wanting to approach that value a. And then the limit as h approaches 0 of f of a plus h minus f of a all over h. So notice here, let's say on this particular problem that instead of me labeling down below as b values, let's say that somewhere in here, I'm going to get rid of a little bit of this so that it makes it prettier. We have this distance h. So that's the difference between a and whatever this b value is over here on the side. Then that would mean that the x value that goes with that particular value is a plus h. Okay, so if the difference is h, then to get from a to that, I'm going to say next b value over, we'd have to do a plus that difference of h to get there. That would mean that up here, that the y value that went with that would be f of a plus h. Okay, so essentially here what happened is this particular formula came about, I'm going to say the same way as the average rate of change formula, with the exception of the limit in the front, in being it's the change of my y's, so f of a plus h minus f of a over the change in my x's. All right, so we notice down below that if we look at the two x values, we have the a and we have the a plus h. If we take the difference in the two, the a plus h was the bigger one, and then minus the smaller one a. Those a's would cancel, and it would give you just the difference of h. And so that's where the denominator in this particular problem came from. Okay, the limit is the thing that's different. You're always going to see a limit when you're talking about an instantaneous rate of change. And what that's doing there is making these points as close together as you possibly can. It's making the distance between the a and the a plus h go to 0, so that we're talking about a tangent line as opposed to a secant line. All right. So one thing you need to know as far as terminology is for a single point on the original function, all of these things mean the same thing. So if you see a problem that asks you for an instantaneous rate of change, that's the same thing as them asking for a derivative, which is the same thing as them asking you for the slope of a tangent line, which is the same thing as marginal. So you're going to see this word marginal, and then we're going to talk later about cost, revenue, profit, things like that. Marginal means rate of change, and then they could be asking you for rate of change in the cost or the revenue or the profit and so forth. So if you see any of these wordings mean the same thing, and those indicate to us that we're wanting to use this formula that we looked up above. Okay, this particular problem, this is a curious problem in that they just want us to set it up, but they don't want us to simplify. So it says, find the limit representation of f prime of x if f of x equals x cubed minus 2x. And then it says, do not simplify the result. If you've had calculus in high school, you may know that later on there's easier ways to take derivatives. So for this one, it's important that they're saying limit representation, which would refer us back to the formula that we just looked at. And so on this particular one, what we're going to want to do is basically use that definition and then plug in the functions that they gave us. And this is a good way to start because it gives us a good setup of these kind of problems. But once again, this one says do not simplify the result. So we want to know, what does f prime of x look like? F prime of x is a limit, and it's the limit as h approaches 0. All right, and then by definition, it's the limit of f of, and then what we did in the prior problem is we looked at f of a plus h. On this one, we're going to leave the a value, which is an x value, general. So this is another way to do it. X plus h, and then minus f of x all over h. The next section over, we're going to talk about the difference between what we do if we know the actual value of x and what do we do if we don't know the actual value of x. So in this one, it's not like they're asking us to find the limit f prime at 7 or something like that where we'd know that value. If you don't know the value, you're just going to replace the a in the formula with an x. So that's what that formula would look like. And then to complete this problem, you'll want to use the function. So this function is x cubed minus 2x. So what is this going to look like? So you keep the limit, and then f of x plus h. That means that in this function, where x is, you're going to substitute x plus h. So you'll substitute x plus h and cube it, and then you'll do minus 2 and then substitute x plus h where the x is. So it's going to look like this. I'm going to start with a parentheses since my x is cubed. Instead of x, I plug in x plus h. And then that's cubed. And then minus 2 parentheses. Instead of x, I'm plugging in x plus h. Okay, now I still have some more of my formula left to go here, but I want to talk about this for just a second. Think of, when you're doing this, using this function and thinking of it as a pattern. The pattern says I'm going to take something and I'm going to cube it, and then I'm going to do minus 2 times that same something. So you're thinking about your function as blanks, and then you're filling in the blanks with whatever they're telling you to evaluate your function at. So in this one, they're telling you to evaluate your function at x plus h, so you're filling in the blanks with that x plus h. All right, now, we talked about a while ago in a problem that if you have a negative here and a multiple piece function that you need to put a bracket around that. And so on this particular one, I'll do that here. So notice our formula has a minus in it, so I need a minus, and then I'll do a bracket here. F of x. F of x means just the function. So whatever function they gave you, we're going to plug that function in. So x cubed minus 2x. And then all over h. Now what they mean is show me what the limit definition of f prime of x is, but show me that without actually simplifying the result. So they want me to write the formula down generally, and then they want me to use the function and plug in, whatever they're telling me to plug into the function. But then at this point, they don't want me to simplify. So in this particular problem, that's going to be what you see as your final result. Okay, once again, this is an important problem. It's basically making sure that you understand the concept and the formula, what a derivative would look like in limit form, but they don't want you to continue on to actually find the derivative. All right, the next question down, what I've done, and this may already be altered in your notes. If it's not, let's go ahead and correct it. It's not that the problem was bad, it's just that the problem was really ugly. And I wanted to start out as far as just an example with a prettier problem. A lot of times when we use ugly numbers, we get lost in the numbers instead of understanding the steps in the problem. So I'm kind of changing this problem up a little bit. We want to find the marginal revenue with respect to the number of units produced when, and then if y'all will, make sure that your problem says 10 units are produced. The revenue function is, and make sure y'all's functions or y'all's note says r of x equals x minus 0.2 x squared. So once again, your notes may have already been corrected, but if they're not, if y'all go ahead and correct them, And we're just doing this for the purpose of making the problem simpler so that we can not get hung up in big ugly numbers. All right, so on this particular one, notice that our wording is different as far as what they're asking us to find. They said they want us to find the marginal revenue. So on this one, when we're looking at what they're asking, marginal revenue, we look at the word marginal and we say, hey, we know that that means derivative. So that derivative means that we want to use our definition. Now on this problem, notice that we want to find the derivative specifically at 10 units. 10 is going to be my A value. So if they give us a value for X, we can actually plug that value in to start with. Okay, so on here, we'll say for this, so we haven't talked about this a lot, but as far as notation is concerned, they're wanting you to find a derivative. So if they want you to find a derivative, say R prime of X. Okay. Now, R prime of X is going to be my general formula, so that would be for any X. If you'd like to, you can find R prime of X first, and then at the end of the problem, you can plug in the 10. Or if you would rather, what you can do is instead of saying X here, you could say R prime specifically of 10. So you can go ahead and substitute in your value of A. That's always a little bit easier to do because you're actually using, I'm going to say numbers earlier so that your algebra doesn't get as nasty. But you can do it either way. If you want to see it evaluated at X first and then plug in the 10 later on, I can definitely send you some notes where you can see that. Or I may even do a problem a little bit later on using that format instead. And then that way you can see an example of both being done. Okay, so on here, R prime of 10, we were going to use our definition. So it's going to start with limit as h goes to 0. And then our definition would be R of, and it would be A plus H. In this case, what is A? A is 10. So we say 10 plus H. And then minus R, and then in the formula, it's R of A. So we know what A is, so R of 10. And then all over H. Now, if you prefer, like if this, I'm going to say messes you up, so to speak, doing this early, you could always have said right up front, this is R of A plus H, and then minus R of A, and then on the next step, substitute in your 10. Okay, so I want to make sure that you do what you're comfortable doing as far as your steps are concerned. All right, now we're going to go to our function. So I've introduced this function x minus 0.2 x squared, and then we're going to substitute in whatever they're telling us to substitute in here. So limit h goes to 0. The first one, they're saying, hey, we want to substitute in 10 plus h anywhere there's an x. So we're going to have 10 plus h. We notice that our function, the very first thing in our function is just an x. And then minus 0.2 times 10 plus h all squared. So the next thing in the formula, we had that negative sign, and then we had the 0.2 x squared. And so we're substituting in where we see the x's, a 10 plus h. All right, then from earlier problems, we know that we have to be careful. Here, we'd want a bracket around this piece since our function is a multiple piece type of function. So we want to say minus, and then we'll put a bracket there, r of 10. So it'd be 10 minus 0.2 times 10 squared. And then all of this is over h. All right, now this particular problem is very representative of the way that derivative problems are going to work as far as the algebra is concerned. So once we've plugged in, I'm going to point out here in a little bit when we get to a step that the last part of this question is always going to work the same way. And if it doesn't, we know that for sure something's wrong. All right, so make sure you keep your limit. H goes to 0. All right, 10 plus h, that's in parentheses because originally there was an x there and I was substituting in the 10 plus h. I don't really have to have parentheses on that, so I'm going to go ahead and remove those. Here, I definitely need parentheses. That's saying, hey, we need to square this function first. So negative 0.2. What does it mean to square that function? So on here, the first thing you need to be careful of is knowing what it's not equal. Okay, you can't apply the square to the 10 and the h. So you can't say it's 10 squared plus h squared. The 10 plus h is a binomial. When we say it's squared, we mean it's that binomial multiplied by itself. So we essentially write it twice. That's what it means. And then y'all remember that we're going to have to FOIL that out here eventually. All right, then we're going to do minus bracket. And then over here, I'm going to go ahead and do this piece. So we have a 10 minus, and then it's 0.2 times 10 squared. Well, 10 squared, that's 100. And then 100 times 0.2, that's going to mean I'm going to move my decimal to the right 2 places. So that's going to end up being 20. All right, and then all that is still over h. All right, from here, we've got limit. H goes to 0, 10 plus h. Okay, what I'm going to do first is I'm going to FOIL that part out. I'm going to leave the 0.2. Okay, in FOILing, I am going to skip one step. When we FOIL, we remember we multiply the first two together. So 10 times 10, that would be 100. And then the next two steps is you multiply the outer two, which would be 10h, and the inner two, which would also be 10h. So as opposed to saying 10h plus 10h, I'm just going to say 20h. And then we multiply the last two, h times h would be h squared. Okay. If you're confused by that, go ahead and write out every single step of your FOIL, and then you can combine, and you'll get the same thing that I do on a later step. All right, now we have minus, and then in here, this is 10 minus 20, which is actually negative 10. All right, I need still that bracket so that we've got the signs being the right thing, and that's all over h. And then we have limit, h goes to 0. All right, and then from here, we're going to go ahead and simplify. All right, so we have 10 plus h. Go ahead and distribute this 0.2 through to those particular values. So negative 0.2 times 100 would be here, negative 20. And then negative 0.2 times 20 end up being 4, or negative 4. And then negative 0.2 times h squared would end up being negative 0.2 h squared. And then negative times negative 10 would end up being positive 10. And then all this is over h. All right, from here, let's see if we can combine some like terms. All right, so we've got a 10 and a minus 20 and a plus 10. So that's actually, if we add the 10s first, 10 plus 10 is 20, and then minus 20, those are all going to cancel out to 0. All right, then from here, we have a like term, a h and a negative 4h. So if we combine those, that'll actually be negative 3h, and then a negative 0.2 h squared all over h. All right, now, this is what I call the moment of truth. At this point, my I'm going to say constant values, the 10, and the negative 20, those values should always cancel. If those values don't cancel, then there's something definitely wrong. The other thing here is in the top, I'm going to ask the question of, do both terms have an h? Yes, both terms have an h, which means I'm going to be able to factor an h out. If that doesn't happen, something's wrong. Okay, so on this step here, and I'm going to say I'm picky about this step, seeing it on an exam or on homework, on a quiz, so forth. So we're going to say limit as h goes to 0. I'm going to factor an h out of the top. So that's going to leave me with a negative 3 minus a 0.2, just a single h there, and then all over h. All right, the reason I want to see you factoring that h out is now if you have a factor of h in the top and a factor of h on the bottom, those two factors are going to cancel out. So now I have the limit as h goes to 0 of negative 3 minus 0.2h. And then now I'm going to say safe to plug in my h of 0. So back at the beginning, perhaps we should have discussed, hey, we can't evaluate this function because if we do, if we plug in h is equal to 0, we notice that we're going to get a 0 in the denominator, and we know we can't divide by 0. So all the way up into this particular point, we've had an h in the denominator. At this point, notice we were able to cancel the h's, and now we don't have an h in the denominator, which means we can plug in. So we're going to have negative 3 minus 0.2 times 0, and that's going to give me just negative 3. So negative 3 was my rate of change for this particular problem, and it was the marginal, I believe, revenue. So on this particular problem, they didn't give us, I'm going to say necessarily, they told us number of units, and I'm going to assume because we're talking about revenue, we're going to be talking about dollars, but we don't know if it's per dollar, $10,000, $1,000, whatever. But on this one, we know here that it looks like we're losing money as far as our revenue is concerned. And so our rate of change here, negative 3, is indicating a definite loss, and then the rate at which we're losing money. All right, so this particular problem, very representative of what's going to happen when we have to find a derivative. It was still kind of ugly just because we had decimals in it, but I'm going to say what happened as far as the algebra is concerned, we saw some good things that we're going to have to do later on in other problems. So one of the good things we saw happen is, what do we do when we specifically see something that's squared? Well, we come down and we write it twice, and then we eventually FOIL it out. That's going to be something that you do a lot. Down in here, what do we do from this step down to the next one? We make sure that we factor an h out. If there's not a h to be factored out, then we know there's a problem or there's an error, and we need to go back and correct that error. All right, let me know if you have any kind of questions about this particular problem. Make sure to let me know, and I'll be happy to go back over it with you. All right, I believe here we're going to look at our last question. And this one, once again, is a type of word problem. And what I'm going to do on it so that you can see the difference in the two types, because some students prefer one over the other, is on this particular problem that I just worked, I discussed plugging in the actual value of 10. And so we did it that way. We said, hey, we can plug in that value of 10. Or I said, hey, you could also just do it in general for x, and then later on plug the value 10 into that function. So I'm going to do this one the other way. And I don't generally do things two different ways, but the only reason I'm doing it here is sometimes you have to. So on the B part of this problem, I'll show you the alternate method for doing your derivative, and I'm going to wait till the very, very end to plug my value in. All right, so let's redo this one, make sure we understand it. It says, that's an ugly word. Epidemiologists in College Station, Texas, estimate that T days after the flu begins to spread in a town, the percent of population infected by the flu is approximated by P of T equals T squared plus T for the day range from 0 to 5. Notice that 0 is included and 5 is included. The first part of this question says they want the average rate of change of P with respect to T over the interval from 1 to 4 days. So pay careful attention to your instructions as far as what they're wanting you to find. They're wanting you to find an average rate of change. An average rate of change is nothing more than a slope. So you're not going to have the limit on this type of a problem. Remember here that my small value is my A, my big value is my B. So we're going to say here, average rate of change is equal. And then on this one, what's the function called? P. So I'm going to say it's P of 4 minus P of 1 all over 4 minus 1. All right, let's evaluate P at 4. So that's going to be 4 squared plus 4. And then minus, I'll go ahead and put my bracket. And then evaluate it at 1. So 1 squared plus 1. And then in the bottom, 4 minus 1 is just 3. All right, 4 squared, that's 16. 16 plus 4 minus 1 squared, that's just 1. 1 plus 1 is just 2 all over 3. And essentially now what I have is 16 plus 4, which is 20. And then 20 minus 2, which is 18, and then 18 is now divided by 3. And so on here we'll have 18 divided by 3 is 6. All right, on this one being a word problem, let's see if we can go through and put I'm going to say units on this at the end. So going back through and looking at what they gave us, notice that they told us that the function represented percent. So it's percent of population, and then that the t represented days. And so this would actually be 6% per day. And if you wanted to write the words percent instead of using the percent symbol, that would be fine. So we notice that at this, I'm going to say between these particular days, that the influx of the flu is growing, and it's growing at 6% a day. All right, then it says find the instantaneous rate of change of P with respect to T at T equals 3. So instantaneous rate of change, that's going to mean, hey, we're finding a derivative now. And with that, we know we need a limit. Okay, so for this one, the derivative we'd be finding is the derivative of P of T. So it would be P prime of T. Notice here that we know what T is. So if we wanted to, we could work the problem as I did the last one, where I actually plug in 3. However, on this one, I'm going to wait to do that until the end so that you can see another method. All right, so that being the case, we're going to have the limit as h goes to 0. And then on this one, it would be P of, normally it would be x plus h. On this one, our variable is not x, but t. So it's going to be t plus h. And then minus P of t all over h. Okay, a couple of things. Do be careful. So on your notation, we're running to use the function p instead of the function f. Also, because we have a variable t instead of x, we're being careful to use that instead. If it ever confuses you as far as where to put things in this first group, you always put your variable first, and then the second piece will always be h. Also, in the denominator, that will always be h, because your limit is always as h approaches 0. So the only thing that you really ever change in this particular formula is your possible variables there, and then your possible function name there. All right, so now we're going to go through and actually use our function. So the limit as h goes to 0, I'm going to have to scroll up above to find my function. It was t squared plus t. So if I'm substituting in t plus h where t was, I'm going to have t plus h all squared plus t plus h. And then minus, I'm going to need a bracket there, p of t, that's always just my function. So that's the t squared plus the t. And then this is all over h. I would say that this is one of the most important steps in this problem. It's also a step where students generally have questions. So I'm going to say if you're confused on this particular step, please let me know, and I can help clarify the plug-in, how to get from the notation using your function into this second piece. All right, from here we have t plus h all squared. So keeping the limit and then doing the t plus h all squared, that means you're going to write t plus h twice, and then on the next step down we can FOIL it. This one we don't really have a need for those parentheses since we're not distributing anything to those, so we're going to leave that alone and just remove those parentheses. On the second part, you do need the parentheses because you're distributing the negative. We're going to go ahead and distribute that negative. And then all this is still over h. So keeping the limit here. Okay, distributing or FOILing, that t plus h part, you're going to have t squared. When you do the outer and the inner, you're getting a th, but that's going to happen twice. So there's going to be 2 th's. And then multiplying at the end, you're going to have an h squared. All right, notice over here, we can go ahead and cancel some things. There's a positive t there and a negative t there, so those can cancel. So we're going to have plus h minus t squared, and then all over h. Now, on the prior problem, I said, hey, if your constants don't cancel out, then there's a definite issue. On this one, I'm going to tell you the same thing, but I'm going to say, hey, if the variable terms don't cancel out, there's an issue. So notice here our variable is t. There's two t squareds. One of them is positive, one of them is negative. If those two don't cancel out, there's something wrong. Now notice that the terms that we have left in the top all have h's in them. Now they can't be combined, so this one's a 2th, this one's an h squared, this one's a singular h by itself, so they're not like terms, but what we can do is we can factor an h out of all of those three terms. So if we factor an h out of those three terms, then we are left with a 2t plus a singular h plus, and notice here we're factoring h out, so we have a 1 left in its place, and then all over h. So remember, this was the piece that I said I was picky about. I want to be able to see you factoring, and I want to be able to see you then canceling. And so at this point, we have the limit as h goes to 0 of 2t plus h plus 1. All right. So up to this point, we weren't actually able to plug the 0 in because there was an h in the denominator. Now we can plug the 0 in for the h. So we would have 2t plus 0 plus 1. And we notice, and I don't want you to be nervous, that there's still a variable in the problem. So this becomes just 2t plus 1. Remember here what we were finding. We were finding the derivative at t. So the notation we should be using here is p prime at t. Remember that what we wanted to find was p prime at, not t, but t is 3. So we come back down here and say, hey, we want to find it at 3. Notice now all you have to do is plug in 3 for the t, and you've got it. So 2 times 3 plus 1. So that'd be 6 plus 1, which would be 7. And remember here, I believe that was percent per day. So on day 3, the instantaneous rate of change was 7% per day. Okay? The nice thing and the reason that I show you this alternate method for doing the derivative is y'all see now you have the general formula for your derivative, and they could ask you for the derivative at any number and you could plug it in here and not have to do this process multiple times for multiple numbers. So if they said, hey, I want to know the instantaneous derivative at t equals 2 days, all you've got to do now is come in here and plug in 2 there for that t value and you've got it. Versus if you'd have plugged in the 3 at the beginning, if they then asked you to do it at 2, you'd have to do the whole process all over with the 2, which is a real pain. All right, you guys let me know if you have any type of questions. This is, I'm going to say, a challenging concept, and that being the case, you need to make sure that you're diligent in straightening out any kind of questions that you have right away so that we can make those corrections and that you don't get hung up on your homework.